Hi, everyone, and welcome to our event today, where we'll be talking about practical data science with Ms. Christina Hill. I'll give a brief introduction of Ms. Christina Hill. As a data scientist within medical devices, research and development, Christina has taken the surgical complication prediction capabilities of the VELIS from proof, hopefully I said that right, from proof of concept to a commercially viable product. Daily, she collaborates with teams across Johnson & Johnson, including MD, Epidemiology, Technology Services, MD Digital Solutions, and external teams like the Mu Sigma and Virtusa. Additionally, Christina contributes to ad hoc projects, including a lab technician, including a collaboration with MD Microbiology to automate routine lab processes that will save our lab technicians hours. Christina is revolutionizing the way that we think about recruiting and retaining diverse talent. Most recently, Christina has led planning efforts for Black Tech Health Hack, a hackathon dedicated to leveraging code and technology for good while promoting a diverse talent pipeline within J&J. Christina has traveled the globe studying languages and cultures and enjoys connecting with people from various walks of life. She's excited to empower young leaders from around the world to develop solutions to our most pressing issues. Thank you for being here, Ms. Hill. Would you like to share a few words?
Thank you. Yeah, that was fantastic. I've never been introduced so well.
All right, awesome.
Yeah, so we can jump right in. I know we've lost a little bit of time and I want folks to get something from this and hopefully we can make it interactive. So I will just start with a brief overview and then we'll get to the hands-on part of the presentation. Sounds great. Okay, so I'll go ahead and share my screen. And I feel like no matter how long you use Zoom, there's always the awkward pause.
No, I agree, 100%.
Okay, let's see.
We can see your screen.
Thank you. Okay, great. So I'll skip the about me. You guys already know, and I'll get right into the overview of the data science pipeline or life cycle. So as a data scientist, I love using this breakdown about how we spend our time. And I usually break that down into 4 categories. So we spend our time defining the problem, cleaning and interpreting data, performing analysis, and then translating that analysis into insights. The majority of our time is usually spent on that cleaning portion. I would say half my time, cleaning, engineering, identifying data sources, integrating them, and really trying to get an understanding of the application, the context for whatever data-driven solution that we're trying to build. So today I'll walk us through hopefully 2 use cases if we have time. One related to a healthcare use case, infant mortality, and then another that's forecasting demand. And hopefully that'll give you a good view of the different types of things a data scientist does and the different applications of data science that could be applicable for you in your studies or in your work, whatever it may be. Okay, so I'm going to skip ahead a little bit. And maybe I'll touch on this, which is the fun, shiny part of being a data scientist or being someone in machine learning AI is really talking about the algorithms. And typically we break down our algorithms based on the problems that we're trying to solve into 2 branches, either a supervised or an unsupervised technique. So we use supervised techniques when we know something about both the input of the model and what we want the output of the model to look like. For example, that could be you have input data that's related to surgical time. You know how long patients stay in the OR, and you want to predict if they'll have some sort of complication, if they'll get an infection while they're there. So you know both the input and the output. Then you would use unsupervised learning techniques when you have data, but there's not really a clear output necessarily. You just have the input data. So that could be maybe you have a group of users for a software, for example, let's say Spotify or something like that. You have a group of users on Spotify and you kind of want to just see what kind of demographics they fall into. Maybe you have a group of folks over here who are really interested in country and might be open to suggestions about new artists in that field, or a group of individuals over here who are really like eclectic and you can throw anything at them. So those types of questions you might use unsupervised learning techniques. Okay. And so I mentioned the data science lifecycle. We spend a lot of our time first in the business understanding, and then from there into the data understanding, then operationalizing the algorithms and modeling. From the sound of that, or when I say that, it could make it seem like the data science pipeline or data science life cycle is linear, but a lot of times it's a very iterative process. So I might get a new data set, talk to the person that owns that data set and knows the context of the problem, and then jump into some code, into some exploration, try out a model, and then decide, what, that might not have been the best approach. Go back to the drawing board, try something else, and keep iterating from there. And you might jump between any of these phases at any time. So something that's really popular in the software world is Agile, and it's also very popular in the data science world, keeping that agile and ability to pivot and to really stay on your toes. In some ways, data science is a science, but it's also very much so an art, trying different things out and figuring out what works for you as a data scientist, which tools, techniques fit best to your applications and things like that. Okay, so before I jump into application, any questions generally before we kind of look at a couple use cases? If not, that's okay. Let me peek at the chat. Okay, perfect. So today, just wanted to give you guys a look at my development platform. Hopefully you can see that on the right-hand side. So today I'm going to be using Domino for no particular reason. There are so many different data science platforms out there that you can leverage. I just happen to have a license for Domino, and so I'm going to be using it today. But for those who are just getting started, I would highly recommend Anaconda, which is a free open source data science platform that has a lot of documentation and a lot of trainings out there for folks getting started. So within Domino today, just wanted to point out a few things. I'll be using Python, the programming language, in Jupyter, which is my IDE, a very common notebook format for data scientists, because you can do that thing that I was saying, play around, go in and jump around within your process, save your notebook, write comments, and it's very easy and iterable to work with as you're going through the process. There are some pre-built libraries and packages that are very common in data science. One that I'll be leveraging today is scikit-learn, amongst many others. All of these listed here are very common. Amazon SageMaker, you might have heard of, H2O AI, and there are more. Facebook has some of their own models, which I'll actually be talking to, and the list goes on. And then last but not least, on the right-hand side, I'll be using some visualization tools, Matplotlib, which helps you visualize your data in the notebook that we'll be using. And then as you get further down the line, building apps, APIs, and things like that around your model. Okay. So I'll stop sharing for just a moment and I'll jump on over to my notebook so we can talk through a use case. Okay. So let me, okay, restart. So here we are. So the first use case that I want to talk through is a time series forecasting use case. So you would use this type of algorithm when you have some data that you collect over time. For example, say you were collecting temperature in Chicago, every day, or temperature in Chicago every hour, and you want to predict what that temperature would be in the summer or something like that. That's when you would use time series. In this case, the data set that we're using is fuel demand. So I forget the exact acronym, but we have a feature called CCGT, which represents combined cycle gas turbines, and we're trying to predict that fuel demand in the turbine. So I'll go ahead and get started. So I'm going to go cell by cell and just talk through what I'm doing. Feel free to interrupt me with questions. Leave a comment in the chat. I'll be looking at that as well. Okay. If I'm talking too fast, or if there's something I need to explain more.
I think you're doing great so far.
Okay, thank you.
All right.
Okay, so we're gonna start by creating this start date, October 8th, 2019, and an end date, May 1st, 2020 for our data set.
Okay.
Then we're gonna import that data set. And I'm just going, cell by cell, each group of code has its own purpose, and I'm just talking you through that purpose. So importing that data set, and we're using that date time to really define the series of our data set.
Okay.
And here we're just retrieving that data set from online. I can actually share this link with you guys if it's something that you'd be interested in playing around more with. I'll just share that to the chat.
Okay. Thank you.
Okay, so now this is where I'm defining all the packages and libraries that I mentioned that I'll be using in this model. So the first one, I'm using Matplotlib, but I mentioned that's a great package for data visualization. The second, Pandas, is great for data frame manipulation. So pulling in the data frame and performing computations on that. And then the last is datetime, defining dates, times, and really mapping out our series.
Okay.
Okay, so we're just naming that data frame with this variable df, and then renaming those columns based on what they should be. When I read it in, they were just kind of numbered, and I'm just giving names to those columns so that we know what we're working with.
Okay.
And so this is just a peek of what that data frame looks like. We have 21 different features. They look numerical, except for this one HDF, which represents the fuel type, I believe. Okay, so just making sure everything looks okay before we jump in and start playing around.
Okay.
So next, we're going to create a new column, that date time that I mentioned. It represents the starting date time and measured increments from there. And then we're going to visualize that data based on that date time. So this x-axis, we start in 2019, going all the way up to 2020. And each of these lines represents a different fuel type. We have wind, we have nuclear, coal, oil, etc., and just the demand for that fuel type over time. So some of these have pretty low demand, some of these have pretty regular demand. This red line here, it doesn't change very much over time. But then we do have this blue line where there's very large changes over time. And so that's the type of data where it could be beneficial to be able to predict demand, because there's so many changes in what you might need to output. For example, putting out too little energy or too much energy could be harmful to business. And so that's where a data scientist would come in and help to optimize. Okay, so let's jump into training a model around that CCGT, that blue line with a lot of fluctuation. So one of the great things about data science is that a lot of folks come into data science from untraditional backgrounds. I myself have a neuroscience background, and I've seen the gamut of all types of people being drawn to data science, especially because now a lot of folks doing research and things like that, they're collecting data as a part of their research, whether it's demographic data or economic data, whatever it may be, collecting that and performing analysis on it for academic purposes. And so I see it a lot being students and things like that being drawn to data science. So for me, as a neuroscientist, I was drawn to some of the computation around brain imaging and spike train analysis. And then I slowly transitioned that over to my job now.
Okay.
But I say all of that to say that because so many people come to data science from different backgrounds, there are a lot of organizations trying to democratize data science, which by that I mean making it as easy as possible to get started from whatever background you're coming in from. So for this particular use case, I decided to leverage Facebook Profit, which is sort of a built-in or pre-built time series forecasting algorithm that you can it's already built, so you can kind of bring your data to it, and it's easily scalable, easily manipulated with whatever problem or question you're trying to solve. So if you
Mhm.
don't quite have the like mathematics, statistical background to build something from scratch, that could be a great way to get started with one of these pre-built algorithms from someone like Facebook or AWS,
Okay.
even some of the scikit-learn
Okay.
algorithms out there.
Okay.
Awesome. Okay, so I'll put that tangent to the side. We have our algorithm imported from Facebook, and now we're just going to prep the data. And so the time series data needs to be in a format with 2 columns, an X and a Y. So here we had, a lot of different types of fuel types. We're just going to narrow it down to that one CCGT. That'll be our Y, and then X is time. Okay, and then again, just splitting the data set X and Y, but then also splitting it into train and test. So a very typical split for modeling is 80% training, 20% test. And we train our models on a subset of the data so that we can then evaluate them against data that we have to see how they will perform against future data that we don't yet have. So it's a way of testing if our algorithm would be able to work in the real world, and any tweaks that we might need to make before putting it into operation and putting it into production. For example, here, basing your financial and demand decisions on an algorithm like this, you would definitely want to test it first.
Okay.
Okay, so we split our data set into that 80% train, 20% test. So let's go ahead and fit the model to our training set. Again, the model is pre-built, so all we have to do is take this profit constructor, feed it our data, and run it to train it. It's very quick, very easy.
Mm-hmm.
And so now we're going to build that data set for prediction. We're going to build an empty data frame, feed it into the train model, and then use that to generate predictions that we can then test against. Okay, so while that's running, any questions so far? Oh, I see a couple in the chat. I'll try and share notebooks. I'm not sure what the best way to do that is, so maybe I can work with the BDPA committee to get that to you guys. I don't have your emails or anything like that, and this isn't public, but I'll try and get the notebooks to you guys.
Yes, I will connect you with Miss Mary Brown. I could share
Okay.
your email address in the chat, and then you could follow up and send her links to your notebook.
Sounds great. Perfect.
Okay, that's perfect.
Okay, so that model is fitted. So this is sort of a visualization of what we've done so far. We had our data from 2019 to 2020. We split it into 80% train, so that's everything to the left, those where those black dots are annotated, and then test is everything to the right.
Okay.
So the red line here on the right are the real values. So we kind of hid that from the model, asked it to predict on some data that we could compare it against. And so the blue lines are the predictions, and we're comparing that against the red lines, which were the real data. And we see that it's a pretty good fit, right? Like it matches those trends of ups and downs pretty well from what the actual data was giving us. Okay. So that's the end of that notebook. This is just about, when you create a model, you can export it, save it. It's like an object that you can come back to and always use. So if you were to get some new data and you want to see like, okay, I trained on 2019 to 2020, but now we're in 21. I can go back to that 2019-2020 model, give it some 2021 data, and compare to see how it's performing now, if that makes sense. Okay. Perfect. Okay, so that's the forecasting use case. Any questions about that before I move on to a different use case?
Anyone in the audience, feel free to come off mute if you'd like to ask any questions. I would just say that so far your presentation has been beneficial to me. I'm also a data scientist in my career, and understanding some of the elements of how you process the data and the algorithms that you're using is exciting for me. So thank you.
Absolutely. Absolutely. And chime in if you have any, insights. I would love to, learn as well as I'm doing this. Because like I said, we're always learning, we're always coming up with new tools and new techniques. So
Right. I particularly like the data visualizations and how you can interpret it as you move throughout the pipeline here.
Yeah, for sure, for sure. It's like that
Yeah,
instant feedback, right?
absolutely. You're doing good.
Awesome. Okay. So let's jump into another use case.
Miss Mary raised her hand. How you doing, Miss Mary?
Hi, everybody. I missed her interpretation, so she showed the result. And so what is your takeaway based on the data that you're looking at there, this visual?
Yeah, for sure. So I'm kind of drawing a dividing line in my mind at this point here, because that's where we cut off the data that we have and separate it into train and test. So we have October 2019 through January 2020, and we're telling the model, hey, let's use, October just through like November data. We'll give you that and see if you can interpret the future from what we give you.
Okay.
So everything to the left was used to train. And these blue, like the blue is basically the model prediction. It's the model learning, reading from left to right. The model is learning as it goes along, October, November, December. And then when it gets to the point where we stopped giving it values, it starts making predictions. And so it used what it learned from October, November, December to make those predictions in January. And so the blue is the prediction, and the red is the real data. And so what I'm seeing here is that the prediction is a pretty good fit for the fluctuations in the model. I see sort of like, I'm trying to describe it. Like these segment, almost if you were in music and you know how music is divided into like 4 beats per measure or something like that. It seems like there are those like beats where you start pretty high and then there's a decline, you come back up and there's a decline. To me, it seems like the model is doing a pretty good job of catching those peaks and lows.
And what did you say the data was that you fed into this?
Yeah, this is fuel demand. So it includes coal, wind, solar demand, but then this the feature that we're predicting on is, let me find the acronym, CCGT, so combined cycle gas turbines, the demand from those gas turbines.
Interesting. So basically we can see the peaks and valleys of fuel demand, which maybe if we were to put days of week underneath there, we might understand the rhythm of this.
Exactly. And so then in the future, now we're in 2021, we can use this model to predict, to communicate with, I'm not in energy, so, take this with a grain of salt, but like talk to the machines that are producing the fuel and say, okay, on this day, you need to produce this much because this is the demand we predict we'll have. And a month from now, we'll probably have less demand. So we can start high and low and things like that. It's a way of anticipating the customer need.
Nice, thank you.
Absolutely. Thank you for the question. Okay.
Hi there, can you hear me?
Yes.
Oh, great. Oh, hi, Ms. Hill. This is, my name is Amaka. I'm new to data science. I'm learning, I'm transitioning to the field. So this is so fascinating. And I'm new, so bear with the question. How, is there an average time, or how long do you test these models to before, I guess, getting to the prediction stage? Is there an average time, or it all depends on the data, the industry?
Yeah, that's a great question, and it really depends. So for time series forecasting, this sort of demand over time, I think typically it's great to have a year's worth of data. Here we're looking at a subset. We're only looking at 3 months, but in an industrial process, it would be great to have that full year so you can predict the demands across the year. But more data is always better. When it comes to building a model, there isn't really a limit or a max or things like that around how much data you have. Whatever you have, typically that's when you'll split into train and test. So I didn't even check to see how big this data set is. I think it's, let's see. Okay, don't quote me. Let's say that this data set has 100,000, for example, observations in it. and then we'll put 80,000 into train, 20,000 into test.
80,
That
20.
ratio is transferable. So if you had 1 million rows, 800,000 versus 200,000. If you only had 1,000 rows, then you would put 800 in train, 200 in test. So it's definitely scalable based on even the demand of the data scientist, how much data you're trying to pull in.
Okay. Oh, wow. Thank you. Thank you so much.
Yeah, for sure. Thank you.
Excellent question and excellent answer there.
Thank you. Okay, so like I said, this isn't really my bread and butter energy. I'm on the healthcare side, so I would love to show you guys a healthcare use case. I'm going to jump over to another notebook, and this will be, completely different application of data science. In that last use case, something that you may or may not have noticed is that the data set was already pretty clean, pretty fresh. Like we could plot it and it looked like we could understand what was going on, but that is not often the case as a professional data scientist. Oftentimes the data can be messy, can be hard to interpret. So I would love to show you guys sort of a working example of a data science problem that I've been working on and was actually a use case for our hackathon last year.
Okay.
So now we might even be able to get into more discussions and questions around that process, especially around data preparation. Okay.
Thank you.
Absolutely. So I'm just going to start out with some packages. So this first grouping of packages really has to do with data frame manipulation and visualization. The second group of packages has to do with sort of data processing or preparation. And then the last to do with modeling. And I'm just going to format a couple parameters for our conversation. So this use case has to deal with racial health disparities, specifically in motherhood and in infant mortality. And so as we jump into this, we'll start to talk through some of the features that we see and some of the context. But just to start you off at a high level, once this loads, there are over 144,000 state level records in this data set and 57 different features that we've collected on mothers of different races across the United States.
Wow.
The features are mixed, so some are numeric and some are categorical.
Okay.
And then the data appears to be sorted by state.
Okay.
Okay, and so let me just walk you through a couple of the features that we have. We have the year that this data was collected, focusing on 2017, 2018. We have the age that the mom was when she gave birth, her education level. We have the number of births and infant deaths in the state, the percentage of low births in that state, things like that. Let's see, graduation rate of the population in that state, percentage of children in poverty. Yeah, so a lot of demographic information, some healthcare information as well around mammography, around diabetes, different comorbidities, and things like that, health index. Okay. So first, let's explore the data. We can look at the distributions of some of the numeric data, see if it's normally distributed or not so normally distributed, things like that. Okay. And so we have all of these different, numeric features, some with higher peaks, some with lower peaks, so it tails kind of all over the place.
Okay.
And then of course we have last here, this sort of 2-peak distribution, which is just the year 2017, 2018. So digging in a little bit more, let's see some of the statistics around this data set. So some things that I would look at going into the data set, if here this count means for that feature, how many patients or how many people do we actually have the information in there for, or is there some missingness? And then of course the mean, standard deviation, min, max, and range of the distribution to get a feel for what the values are. It's important to look at this because sometimes there are errors. So let me try and find a let me find if there's an example of one that could have an error. So for example, a lot of these are percentages, but I think there is a BMI here. Let me see if I can find it. That's a common one where maybe a nurse was collecting BMI information and just added an extra digit to the number. So instead of having like a 24 BMI, you have like a 241 BMI or something like that. That's obviously off the charts. And so that's the type of thing I would look for in the data as well.
Okay.
Okay, so we have that numeric data that with the distribution, but we also have some data that is categorized. So I mentioned we have state level data. There are 32 states represented in the data set, with Texas being the most populated. We have race, where we, I believe that there's white, Black, and Hispanic in this data set, maybe also Asian. We have the age of the mother, which is kind of grouped into buckets. So we have these ranges. Here, the top range is 25 to 29. But we also have lower ranges and higher ranges. So mothers, I think from like 22 to 24 is one range, and then from 30 to 32 is another range, and they're grouped like that, so on and so forth. Of course, education level. And then this one here, some of you might be familiar, but ICD-10 codes are commonly used for their diagnosis codes. So when you go into the hospital, the nurse or the doctor would assign a code or an ICD-10 code to the reason that you were admitted, or for billing purposes, things like that. And so here, the most common ICD-10 code is that there were conditions originating in the perinatal phase, so right before or after birth, and that's the reason why these mothers are in the hospital, or why there might have been a mortality.
Okay. Wow.
Okay, and then last but not least, unfortunately, some of this is a little sad, but we're gonna push on. So the death rate here, which I see rate and I think number, so it surprises me a little bit that it's here with some of these categorized features that have categories. And so that's something we'll have to take a look at to make sure that it's been classified in the correct bucket. Okay. Let me check the chat. Okay.
Yeah, I got you.
Thank you. I saw a few, so I just wanted to make sure there are no questions.
All right, cool.
Okay, so let's look at, let's start with these features that were categorized, that last chart that we went through. So here, again, I'm scrolling through, and on the right-hand side, I'm seeing numbers, but then I'm seeing this tag, unreliable. That could mean a number of things. That could be that, you know, they collected this data from somewhere else, and maybe it's accurate, maybe it's not. That tag could mean that that number changes sometimes, and so this is an average. It could mean a lot of things. And so this is when, as a data scientist, it's very rare that I'm working alone. I would talk to like an epidemiologist, I would talk to a nurse, talk to a surgeon to try to get a better understanding of the data, how it's applied, how it's collected, so that I can process it accurately. Okay, for now, with this column, we're going to treat it as a number, and we'll get to how to do that later, but just wanted to point that out. Instead of a categorical feature, we'll treat it as numbers. One other thing that I'll point out when it comes to some of these categorical features. So here we talked about how this is state level data. Texas is the most represented state. Let's see, representing 30% of the entries in this population. Okay. And there are some states that have very little representation. So here we see South Carolina is less than 1% of the data set. And so something that we might try with these, so with these populations that aren't as represented, Massachusetts, 0.009% of the population, feeding that information to a model might be, could be tricky, because it's not very generalizable. It's not very represented of the people in Massachusetts, for example. So something that we might do to get around that is combine some of these features that have very, very low representation into like an other category or something like that, so that the model isn't sort of overfitting or training on very little data in a place and creating results that aren't quite representative or generalizable, especially in the healthcare world. Okay. Hopefully that makes sense. That's the main thing that I wanted to point out here with these categorical features.
Okay.
Okay. So I'm gonna close this down. So we're still in that data exploration, data cleaning phase. Remember I said this is sometimes over half of the work of a data scientist. So bear with me while we get through this before we can get to the fun part of modeling. So next we're going to look at some of these features and how they relate to each other and their missingness and things like that. Okay. So this is a visual representation of the data frame where black represents in that row that patient does have an entry, and then that white or cream color is in that row a patient is missing an entry. And so I see here that there are kind of 3 features where there's no data at all. These would be things that we would throw out from the model. For whatever reason, they were included in the data set, but that was probably an accident. And then here, let's see if I can get you guys to see this. Let me know if it's too small, but here, if I turn my head to the right, I see that there are kind of duplicate columns. There's sort of this cutoff point here where half the data set is in this group of columns and half the data set is in this group of columns, but they have the same name. So they say children in poverty, Hispanic, white, and Black, but they're kind of duplicated. So there are 6 columns instead of 3. So that's something we can explore as well. Why were they separated? Are these really different columns, or is this the same data and can it be combined into one feature? Okay. And then this is just sort of a numeric representation of that same graph, but here visually we can see where the missingness is, and sometimes it's good to quantify. So let's see, in that children in poverty feature, we have sort of 66% missing Blacks, 59% Hispanic, 51% missing white, and then 68 again. So the same level of missingness in these features, which is probably another indication that they could be the same data. But it's good to see, like, okay, how much is missing? And then we can't feed missing data into a model. So if we took that out, how would that affect the population size and the number of people who would benefit from this tool? Okay. So looking into those columns that look the same, one thing that I would love to check is the distribution. So, 2 different columns with what looks to be the same name, but they are annotated differently, but then they have the same distribution. Again, that's another indication that this is probably same or similar data and can be combined. And then just one more sample from that collection of features. Again, very similar distributions, similar peaks and similar valleys, probably the same data and just got categorized weirdly and can be combined into one feature. Okay, and now let's take a look at just really getting granular at like an example row from this data set. So picked a random number. This is a mother from Georgia falling into the 20 to 24 bucket, and just making sure that these values kind of are what we expect. So a lot of these features are percentages. And so we would expect a number between 0 and 100, for example. Income, 15,600, that sounds like a reasonable income for the United States. If it was excessively low or excessively high, that might be something we'd look into. Here, these are those kind of columns with emptiness, and I see it here as well. This says none or not a number. There's nothing there. Yeah. Okay, just scrolling through and checking and making sure we can really understand this data. Okay, so now based on what we've learned and absorbed about the data set, this is when I would move into cleaning. So, take everything that you've learned, take all the conversations that I would have with nurses, physicians, epidemiologists, and try and clean the data set in a way that makes sense and makes it more accurate for preparation. So I'm just going to create another variable here called cleanDF, and we're going to work with that from now on. So I mentioned already, but we have these pairs of features that seem to be separated into 2 separate columns. We're just going to merge those into 2, merge them and combine them, and then drop one of those features from the data set. And so here we're just checking, we dropped, so this is sort of a list of lists within these 2 pairs. We kept the one with the hyphen, we dropped the one with the parentheses, and here we're just confirming that. after we merge them together. Okay, and then I talked about, again, that column that seemed numeric, but it was categorized as a categorical feature because it had that tag, that unreliable tag. So what we're going to do is take away that tag and just keep the number and then use that number in modeling. Okay, now that we've cleaned up that column, we can change its data typing to be this object one, which is used for categorical features, to float, which is used for numeric. And then for this yearly data, since there's only 2 years in the data set, we're actually going to switch that from numbers to an object so that it's splitting the data set into 2 categories, a category for 2017, category for 2018. Okay.
2018.
Mm-hmm. And now that we've removed some of the messiness, the noise from the data set, we can go through and get rid of any rows with missing data. Or excuse me, not any rows, any columns with missing data. So those 3 columns that had nothing in them, we're taking those out now. Okay, so now, going back to the cycle, we did some data exploration, we did some cleaning. Now we're going to go back to data exploration. It's definitely a cycle. So after we've done the cleaning, we can look at what is the visual representation of the data set look like now. So for those columns that we cleaned, percentage of children in poverty, they look a lot better. There's not that split anymore, right? And we don't have those columns anymore that were completely empty. We dropped those from the data set. So this is looking like a more complete and accurate data set now that we did that cleaning. And we can now go in and examine the distribution of some of the numeric data a little bit more closely. Earlier, we looked at it sort of all together, but we can go feature by feature, look at those distributions and decide if we want to perform any type of cleaning or formatting on that data. And so let me open this up a little bit.
Time check for you, Ms. Hill. It is 4:52. I know we started a little bit late. I'm willing to stay over. This is a great presentation, so please continue. And if there's any questions,
you so much.
Folks, you can feel free to put it into the chat. Thank you.
For sure. Okay.
No, you're doing good. Thank you.
Thank you. So typically, a lot of machine learning algorithms expect this sort of Gaussian curve, a bell curve, what you'd see, when we took standardized tests and all that stuff, and they talk about percentiles, that type of distribution. But obviously, real world data doesn't often fall into that. We'll have data with high peaks early in the distribution and then right tails or left tails. We might even have something like this, where it's sort of 2 peaks, or a larger peak and a smaller peak towards the tail end. And so something that we could consider doing is normalizing this data, which is a mathematical process to take distributions that aren't normally distributed and get them to look like a normal distribution before feeding them into the model. And that does a lot of things, but it often helps your machine learning algorithm not overfit to one specific feature or interpret results incorrectly sometimes based on it having that expectation that the data will be normal when it's fed into the algorithm. Okay, and then this is just a cute little visualization that I figured I'd share with you guys, but this is a relationship map between the features in the data set. So for example, this branch here, we have that children in poverty feature, which actually has a strong relationship with the percentage of mothers that might have driven alone to the hospital, which is interesting and something that we can keep in mind as we're building out this model. Sometimes in cases where features are very similar to each other, we can keep one and throw the other one away so that there's not too much information of the same type being fed into the model, and there's more of a varied distribution of information that the model can base its decisions on. Okay. So let's see. So I'm going to jump a little bit forward, just keeping time in mind, to some more transformation before we get into the algorithm itself. So we talked a little bit about missing data. And here we're taking a look at row by row, what percentage of patients have missing data for each of these features. So we have the age of the mother for every row, but we don't always have the chlamydia rate in that state, or we don't always have, let's see, another one that's high. The percentage of mothers that received HbA1c while they were in the hospital. That's one that seems to have a lot of missingness. And so we'll tend to throw away features that aren't very reliable, that we can't reliably get information on, and only keep the ones that we have, a good majority or consensus of information on.
Okay.
So here I picked this threshold of 0.25, and that means that any feature that has 25% missing or more, 25% missing data or more, we're going to get rid of. So that would include any of these features that have, 69, 70% missing. We're not going to include those in the model, but anything below that, for example, the violent crime rate in the state, we'll keep that information and we'll just throw away the rows where that missingness is. Hopefully that makes sense. Okay, so that's what I'm doing now. I'm, excuse me, I'm removing any column that has over 25% missing. And those columns, just listing them out here to make sure that they are what I expect, which they are. And then finally, just looking at the shape of the data frame now that we've done all that cleaning. So after we get rid of all the missing columns that we want to get rid of, the missing rows that we get rid of, we started with 144,000 patients, narrowed it down to 82,000 patients, and this is a complete data frame. So now we can feed it into the model. So oftentimes there isn't a best fit or one algorithm or one way of cleaning the data set that is perfect, will perfectly solve your question. Like I said, it's kind of an art. You play around with different things, different techniques, different data processing, different algorithms until you find something that works. But just for the demo, I decided that we would use a k-nearest neighbors classification. So for anyone that's unfamiliar with k-nearest neighbors, I have a cute little visualization that speaks to what that algorithm is doing. But it's taking all of those features, I think I said 37 or 47 features, reducing it down to however many dimensions you decide to give it. And then for your test population, so here we represent that as this box with a question mark, that's the test population. Compared to the training population, we say, okay, how far away is it from group A versus group B? We calculate that distance, find the shortest distance and assign it to that cluster, if that makes sense.
Makes perfect sense.
Awesome. Okay, so that's what we're doing now. We're building that k-nearest neighbors classification. Just first, we're building out our list of features. So we have these categorical features, continuous features, and then our label. So in this example, we have group A, group B. In our use case, in our real world use case, we're going to use the age of the mother as a way to differentiate between groups. So we had about 5 groups there, 20 to 22, 23 to 29, 29 to 30, those groups. We're going to assign a different label to each group and then feed our testing data into the model and then try and predict on feed our training data into the model and then try to predict on our testing data if we can accurately calculate that age range. So in the real world, this could be a tool. Maybe it's to classify whether or not a mother has a high-risk pregnancy using some of her demographics. We could, here, we use the pseudo for that is age, but it could, have that application in the real world. So that's, a framing of this problem in context, if you will.
Okay.
So here we're just final touches before we get to our model. Taking some of the textual data and turning it into numerical data. We do that by, let me scroll back up so I can talk through this in a way that makes sense. Okay, so for this state level data, we have 30 states represented. What we'll do is create a column for each of these states and give each row 1 if that person is from Alabama, and each row is 0 if they're not. For the Arizona column, we'll give a 1 for the people in Arizona, 0 if they're not. And we'll go through the data set like that, turning these categories or text into numbers so that we can feed them into the algorithm. And that's called one-hot encoding.
One-hot encoding.
So we perform our one-hot encoding. And this is truly our final data set that we're feeding to the model, where everything is represented by numbers. We have all of our features, categorical and continuous, ready to go into the algorithm. We split that data set into train test split, still using that 80-20 ratio. And then we fit the model. So we have this k-nearest neighbors classifier. In the last example, we used a Facebook algorithm. This one, we're using a scikit-learn algorithm to fit to the train set and then predict on the test set. Here, I'm using a metric accuracy. So how accurate was the model in assigning the right label to the test data, and we compare that against the real world data to give us a score. So in this case, our model is at about 73% performance, which is pretty good. And we still don't know a lot of missing factors in this data set. We still have a lot of improvements to be made. So like this as a baseline starting point for production level data science algorithm would be really good. And you could continue iterating to make that accuracy higher.
I just want to take a quick break here. I know we're at 5 o'clock. If any of our attendees would like to step and experience other conference events, please feel free. I want to allow Ms. Hill the opportunity to finish because I know we had some technical difficulties in the beginning. Ms. Hill, how much more time do you think you would need?
That's actually the end. So that was the complete modeling process.
Awesome.
And I was just going to take questions if anybody had any.
Well, that's perfect then. If anybody in the audience has questions, this will be an excellent opportunity to either come on screen or put your questions in the chat. I see Ms. Amaka has raised her hand.
You said that perfectly. Yeah. Yes, I have a question. As someone transitioning to the field, is there any resources that you would recommend? I've been doing online and will be taking some courses in a couple months, but what resources you think have helped you? I know you're a neuroscientist, but for someone that's transitioning, is there anything you recommend?
Yes, absolutely. So you mentioned courses. I think there are so many great courses out there. Coursera, Udacity, all of those sort of online learning platforms have really great ones. I would also recommend blogs, data science blogs. So there's Toward, I think it's Towards Data Science.
Oh, yeah. Okay, I joined that one.
It's a great blog for reading data science content and seeing how different people approach problem solving and modeling. Okay. I would also recommend just reading documentation. So until you get to the point where you are the type that wants to build your own algorithms from scratch, a lot of times you will use sort of built-in or locked-in loaded algorithms. And so they oftentimes come with documentation. So this is an example of clustering documentation, and it talks through the different clustering algorithms, gives you example use cases and even example code. So that's another great place to start with the documentation from different libraries.
I haven't heard of this one. Thank you.
Absolutely.
A lot of people are excited about the presentation and they would like access to your notebook. So I've asked folks to drop their emails in the chat and we'll make sure you get them afterwards and you can follow up with folks to give them the notebooks.
Sounds great. Yep, can do.
If that's all the questions, we will begin to close out. Just would like to say thank you to Ms. Hill today for the excellent presentation. Shout out to all of our attendees for coming to the BDPA conference today. There were a lot of gems dropped, a lot of nuggets is what we like to call them in this presentation. I hope everybody was able to take something home with them that they can learn. And in the future, we look forward to seeing you do great things, Ms. Hill.
Thank you all for having me.
All right, awesome. So I hope everyone has a great conference experience and thank you for joining our session today. Awesome. I am taking down some emails really quick out of the chat, and I will follow up and send an email for folks who would like to access the notebook. Okay, looks like I've got 4 or 5 email addresses here. Just from a data science perspective, from what I do on a daily basis and what I've learned about data science, I think this presentation was very thought-provoking. I think it was very in-depth, and I really appreciate it. I think I learned a lot, especially in terms of large data sets, cleaning data, modeling, and algorithm visualizations even. So there was a lot of great things about this presentation. So I just want to say thank you for your time today.
That means so much. Thank you for real.
All right.
All right. Have a good
All
one.
right. See you all later. Later, everyone.